Hello friends, welcome. So today we are going to discuss a very amazing problem, and it is the problem number 7 of Pathfinder fluid mechanics. And it's a very amazing problem, I must say. Here we will be encountering the equilibrium of a cylindrical vessel, and it's a very amazing problem. I found it very amazing, and let us discuss the problem, friends. So here you can read the problem. I will just explain it here. I have not taken the problem, and here I have drawn the figure. So it is given that water is filled in a cylindrical vessel. So it is a cylindrical vessel of base radius r. Okay, so we have got a cylindrical vessel of base radius r. It is given. Now the length of this vessel is l. Okay, the total length of this vessel, okay, the total length of the vessel is l. The total length of the vessel is capital L. Okay, now a fulcrum is placed at the middle of the cylindrical vessel, you can say, and then water is filled. Water is filled in that. Okay, so what would happen? Water would exert some hydrostatic pressure on the piston, and there is a piston, a piston having some mass is connected with a spring of force constant K and natural length L naught. It is given that the spring is having a natural length force constant K and natural length L naught is given, and the value of L naught was given 15 centimeter, and L by 2 is approximately 16.5 centimeter. You can check the data given in the problem, so I have drawn it like this. So delta x, we will measure the delta x, that is the piston would be surely displaced by some amount. Now that amount you can written as delta x, and that is measured from the L naught, that is the equilibrium distance. The equilibrium distance, we have been measuring all things from the equilibrium distance. So this is delta x. Okay, now you can say that, okay, now we have to find the value of this h, the amount of water which is present here, such that all of the whole system remains horizontal, okay, or it does not rotate. So there can be other methods of solving this problem, but here we will be tackling it using the concept of center of mass. So here first of all, let us write the pressure equation on the piston. I hope you understood the situation, and I have drawn the diagram very clearly, so that you can understand where all the distance, because the distance is the main thing we have to encounter in this problem. So here at the surface of the water, we can say the pressure would be P naught. So at this level, the pressure would be P naught plus rho gh. So at the bottom level, it would be P naught plus rho gh plus rho g into 2r. Okay, now here we can say that since it is open, there is a hole here, we can say that this would be an isobaric process. The pressure would always be equal to the outside pressure, p naught, p naught, p naught, p naught. It would always be p naught. Okay, so here the pressure is p naught, and now we would write the equilibrium equation on the piston. Here you can say that the equilibrium equation here would be, here the pressure is p naught plus rho gh, and at the bottom the pressure is p naught plus rho gh plus 2 rho gr. Now from this side, the forces acting here are k delta x, and the forces and a pressure of p naught. Okay, so here we can say that uh, now we know that the mean pressure would be acting through the middle, somewhere at the radius r. Let us say this distance would be r. This distance would be r. It would be acting at the middle point of somewhere at the mid, or anywhere. It could act anywhere. So the net pressure that would be acting would be the mean of the pressure at the top and the pressure at the bottom. You can also find it by integration. So here I have done that procedure. So here you can see that P naught minus rho gh plus P naught rho gh plus 2 rho gr, and then I divided it by 2 to get this result. Now here I have written the equilibrium of the piston. The equilibrium of the piston could be written as Pwa is equal to P naught a, the force, plus k delta x a, and here the delta x value could be written as rho g h plus r into pi r square, which is the area, and k divided by k. Okay, so this is the value of delta x equilibrium. Now here comes the most important part of the problem, so let us understand. So in the problem, it was given that when the mass of the water would be equal to the mass of the piston, the system would be horizontal. So we are going to tackle that here. Okay, so you can see that the water is present in this whole volume. Okay, in this whole volume water is present. So, where would be the center of mass of the water? It would be at the central axis. Actually, it would be somewhere above the central axis, because some amount of water is present here. So, the center of mass would be somewhere above the axis. But this height would be very less, as this amount of water is very less. So, we would approximate it to be at the central axis of the cylinder. That is, the center of a mass of the water and the center of mass of the piston are on the same level. If this height was very large, if I say that suppose the height was very large, then we have to consider the shift in the center of mass. But that too would not affect anything. Okay, yes, but the distance would change. Okay, suppose if it would be somewhere near this. Okay, the center of mass would be somewhere here near this and this. Okay, so it would be shifted, so it would not be exactly at the midpoint, but the location would be somewhere shifted, somewhat shifted. But here, because the height is very negligible, or the amount of water in that orifice is very negligible, we can easily approximate it to be at the uh, center of the central axis of the cylinder. Okay, so first, let us approximate it to be at the central axis of the cylinder. We can say that it can be approximated to be the center of the cylinder. Now here we would write the torque both due to the mass of the piston and due to the mass of the water. So that analysis has been done here. So please see the diagram very carefully. So this is the fulcrum. Okay, this is the fulcrum. Now from here to the last point, the distance is L by 2. From here to this point, the distance is L naught, and this distance between the two points, that is Q, let us say this point is Q, which is the location of the center of mass of the piston, and this distance is delta x. So the total distance, the total distance can be written as L by 2 minus L naught plus delta x. So OQ, the value of OQ would be L by 2 minus L naught plus delta x. I hope you understood what I wrote here. Okay, so now similarly we would do here, that this distance from here to this fulcrum is L by 2. Now from here to here the total distance would be, because we need to find the center of mass, of the water, it would be at the midpoint of the total length. This total length, the midpoint of this total length would be the location of the center of mass, and that only I am going to do here. Okay, so here we can say that, okay, so the value of op could be written as the total length, which is L by 2 minus this length. Now this length is what? This length is half the total extent from here to here. The half of this would be, because it is the center of mass is located exactly at the midpoint of this total length, and this total length can be written as this length plus this length plus this length. So I have written it here. Okay, the total length has been written. Okay, the total length has been written, and the half of that is L by L minus L naught plus delta x by 2. So I have written that, and now we would equate the torque. So let us say that this angle is alpha and this angle is phi. Okay, this angle is alpha and this angle is phi, and it would produce a net equal torque, so that no rotation of the system would occur. So here we can write torque due to water is mw/rw. Now what is rw? This distance is rw. Okay, you need to consider the triangle OPCOMW and OQCOMP. Okay, now considering both of these triangles, we can write torque due to water, tau W, as MW/RW sin alpha. Now from the triangle we can say that RW sin alpha is OP and RP sin phi is OQ. Now putting all these things in equation, we would get equating them, we would get MWOP is equal to MPOQ. Now MW is equal to OP, MW is equal to MP, which is given in the equation. The center of mass is also the same. That's why we will say that OP and OQ would be equal from the figure. Now what we have to do, we have to just equate OP and OQ. Now from the figure we can write the values of OP and OQ. So seeing the figure, we can write the values of OP and OQ. So OP is L by 2 minus this distance, L by 2 minus this distance. Okay, the total distance is this, and we need to find this one. So L by 2 minus this one. Okay, I hope you understood what I have written here. So L by 2 minus L naught by 2 plus delta x. Okay, now here from figure we can write all these things OP, and OP would be this, and similarly we would write OQ from the figure. Okay, now equating both of them we can write the final answer. Okay, the calculation has been done here. The final answer would be this, the value of H would be this. I hope you like the solution, and it was a very amazing problem, I must say. And thanks for watching the video.